Hello there, friends and students. Welcome to my high school physics video tutorial. This time, I'll be discussing two problems involving the dynamics of rotational motion. So just stick around, watch, and learn. So for our question, five rigid objects of different shapes are started at the same time focusing from the same point in an incline as shown below. Which one reaches the bottom of the incline first and why? We will assume that the objects roll without slipping. Choices are letter A, a solid sphere, letter B, a hollow thin-walled sphere, letter C, a solid cylinder, letter D, a hollow thin-walled cylinder, and letter E, a thin-walled circular disc. So our solution to this question, we will base it on the assumption that the objects are just rolling without slipping. That means that we will assume that they are not sliding along the incline. All right? In addition, since the objects are rigid objects, as well as the surface of the incline is also assumed to be rigid, that means that the kinetic friction will not be doing any work on any of these objects. And that will allow us to apply the law of conservation of mechanical energy, which we will describe that at point 1 or at level 1, all right, each object has zero kinetic energy because they started from rest. And each object also has gravitational potential energy denoted by capital U at level 1. That's U1 equal to, of course, mass times acceleration due to gravity times the defined vertical height. All right? As usual, we take the what do you call this? The foot or the bottom of the incline as our reference in defining gravitational potential energy. All right. Now, when each object is about to reach point 2 or level 2, that means before reaching the bottom of the incline, we say that the gravitational potential energy of each object is equal to 0. That's U sub 2 equals 0. And that, since they are rotating, all right, they are rotating or rolling, by the time that the object reaches the bottom, it should acquire an angular speed omega. Angular speed omega, which is equal to the translational speed of the center of mass of the object divided by the radius. And we also emphasize, okay, according to the law of conservation of mechanical energy, that upon reaching level 2, all right, the kinetic energy K2 is just equal to the sum of the translational kinetic energy of the center of mass of each object plus the rotational kinetic energy about an axis assumed to be at the center of mass. We now proceed to our solution. First, we have this formula for the moment of inertia of the object about its center of mass. All right. It is equal to a number represented by letter C multiplied by the mass of the object and the square of its radius. That letter C is any number that is equal or less than 1. All right. And our goal is to determine that value of uh, C, so that we will be able to come up with the greatest value for the translational speed of the center of mass of the object, right? And since we consider the law of conservation of mechanical energy, which says that the sum of the kinetic energy and the potential energy at the start, level 1, must be equal to the sum of the kinetic energy and potential energy at level 2. Okay? And expressing each of this form of energy, where kinetic energy at the start is 0, while the potential energy of each object is mgh. That's equated to the kinetic energy associated to the translational motion. Express that as 1/2 mass of the object multiplied by the translational speed of the center of mass squared, all right, plus the kinetic energy associated to rotational motion, and that is equal to 1/2 the moment of inertia expressed as c times m times the square of the radius r, and that is multiplied, of course, by the angular speed square. But the angular speed has already been replaced by b sub cm, the translational speed of the center of mass, divided by the radius r. Of course, the gravitational potential energy at level 2 is equal to 0. And if you're going to simplify this equation, we will now arrive, all right, at our working formula for determining the translational speed of the center of mass, or v sub cm. V sub cm is equal to the square root of 2gh divided by 1 plus c. Okay, this formula has been derived. If you notice, we were able to cancel out, all right, we were able to cancel out the mass, capital M, and the radius of the object, capital R. This means that this translational speed of the center of mass is independent of the body's mass, capital M, as well as the radius, capital R. All right? And having these values for the C of each object, all right, we have for the hollow sphere, it is 2/3. For the solid sphere, it is 2/5. For the solid cylinder, it is 1/2 or 1/2. For the hollow cylinder, it is equal to 1. And for the thin-walled, what do you call this, circular disc, it's also equal to 1. And checking this formula for BCM, okay, we will able to deduce that indeed the smaller the value of C, the greater is the value for the translational speed of the center of mass. And we therefore say that the solid sphere will reach the bottom of the incline first, ahead of all the other objects. All right? So our answer is also based on the concept of conservation of angular momentum, which says that if the angular momentum is conserved, meaning if it is constant, all right, uh, the object which has the smallest moment of inertia, in this case it is the solid sphere, will acquire the greatest angular speed, and therefore the greatest translational speed of its center of mass. So that's it. We were able to answer the question already. The question reads, a primitive yo-yo has a massless string wrapped around a solid cylinder with mass of 200 grams in a radius of 2.00 centimeter. You hold the free end of the string stationary and release the cylinder from rest. The string unwinds but does not slip or stretch as the cylinder descends and rotates. Using energy considerations, find the speed v sub cm of the cylinder's center of mass after it has descended a distance each equals 1.00 meter. Alright, so for our initial solution and analysis, alright, VCM refers to the speed or velocity of the center of mass cylinder. So that's what we are asked to determine. We first identify, all right, the gravitational potential energy at point 1 in the diagram. So we say that the gravitational potential energy U1 is equal to mgh. Okay? While at point 2, right, when the yo-yo reaches this point 2, it will have no more gravitational potential energy. So U sub 2 will be equal to 0. At point 2, we also describe the kinetic energy. Right? The kinetic energy K2 of the yo-yo is just equal to the sum of the kinetic energy due to the translational motion of the center of mass of the yo-yo, and that is expressed as 1/2 mass times the square of the speed of the center of mass of the yo-yo, then plus the kinetic energy that is due to the rotational motion, that's expressed as 1/2 multiplied by the moment of inertia of the yo-yo times the square of the angular speed omega. This angular speed is just equal to the linear speed v of the center of mass of the yo-yo divided by the radius of the yo-yo denoted by letter r, while the moment of inertia, all right, since we're talking about a solid cylinder, the formula for the moment of inertia of a solid cylinder is equal to 1/2 times the mass and the square of the radius. So this is the moment of inertia, all right, of the center of mass of the yo-yo. So if you're going to substitute the equivalent of omega in this equation, which is v sub m or v sub zn divided by r, right? And substitute also the formula for the moment of inertia of a solid cylinder, okay, in this term, then we will be able to express the total kinetic energy of the yo-yo as being equal to 3/4 of the product of the mass and the square of the linear speed, the center of mass of the yo-yo. All right. In order for us to determine the linear velocity or speed, the center of mass of the yo-yo, we are applying the law of conservation of energy, all right, which goes like this. The kinetic energy, position 1, plus the gravitational potential energy use of 1, all right, must be equal to the sum of the kinetic energy when the yo-yo is at point 2 plus its gravitational potential energy use of 2. All right. So we say that point 1, the yo-yo has zero kinetic energy, but it has uh, gravitational potential energy as mgh. Okay, equate this to the total kinetic energy of the yo-yo at point 2, which we earlier expressed as 3/4 of the mass and the square of the linear speed of the center of mass of the yo-yo, right? At point 2, we emphasize that the gravitational potential energy is 0. So we come up with a working equation for determining the linear speed or velocity of the center of mass, the yo-yo, being equal to square root of 4/3 multiplied by acceleration due to gravity and the height h. In a short while, we're going to calculate for this uh, speed b sub cm. Moving on with our calculation for the translational speed, the center of mass of the yo-yo, whose formula is equal to the square root of 4/3 the product of g and the height h. So substituting our given data to this formula, we will get the speed or translational speed of the center of mass of the yo-yo that is equal to 3.61 meters per second. Alright, so if we try to evaluate this calculated speed of the center of mass of the yo-yo, you will notice that the value that we obtained is lower than the speed, all right, than the final speed of an object that is not attached to a string like the yo-yo here. For example, if the object is just dropped from rest and travels a distance h, then the formula for determining the final speed, all right, or the linear speed would just be equal to the square root of 2gh, right? So, in this situation, inasmuch as the object is undergoing translational as well as rotational motions, we say that part of the gravitational potential energy of the yo-yo that it has at the beginning or at level 1, point 1, part of the potential gravitational potential energy is in fact converted to what we call rotational kinetic energy. So as a consequence, the value for the uh, kinetic energy translational, okay, will not be equal to the original gravitational potential energy. Hence, the corresponding final speed, in this case, the speed of the center of mass, the yo-yo, is much or is lower than what we expect if the yo-yo behave like a freely falling body. Okay. Furthermore, we emphasize that if a rigid body such as the yo-yo here is translating and rotating at the same time, meaning it is moving in a straight line, meaning moving uh, linearly or translationally, and at the same time is also rotating, we describe the total kinetic energy as the sum of, the kinetic energy that is associated to its translational motion, specifically of the center of mass of the body, plus the rotational kinetic energy about a point which is considered the center of mass. For question number 2, we have this illustration. Okay, the problem reads, a light non-stretching cable is wrapped around a solid cylinder, right? This is the solid cylinder whose mass, capital M, is given, all right? And it has specific radius labeled capital R. It's also given. And the cylinder rotates with negligible friction about stationary horizontal axis. So we disregard the friction, all right? As the cylinder rotates, all right, there is negligible amount of friction, okay, between the cylinder and the axis or the material that constitute the axis of rotation. Now the free end of the cable is tied to a block of mass small m here, and this mass of the block is also given. At first it was held at rest and then released. It starts to accelerate down, okay, and travels a distance each until it reaches, or just about to reach, point 2 with a certain linear or translational speed v. All right. Uh, this distance h is also given. Now, this happens because the what you call the cable unwinds. All right. The cable is originally fastened to this cylindrical or solid cylinder that acts something like a pulley. All right. So as the block starts to accelerate, naturally, the cable unwinds. Okay, and we have to assume that when it unwinds, the cable does not slip. All right, it does not slip. So we say that the solid cylinder is just rotating or rolling without slipping, and at the same time, the cable does not stretch. Right? So, in a short while, we are going to determine the what you call the forces acting on both the block as well as the solid cylinder we have our vector diagram in a very short while, and we will also proceed with our calculation. We have here complete description of our problem. Okay, so the variables, capital M is given, the radius of the cylinder is also given, the mass of the block is given, the height H. Right? The question specifically is asking for the acceleration of the polling block and the tension in the cable. So for our further analysis, okay, we have here the vector illustration or diagram. First, on the cylinder, all right, these are the forces acting on the cylinder, all right. The horizontal axis, all right, is exerting an upward force on the solid cylinder, and that is what we mean by the normal force that is directed upward. That is opposite to the weight of the solid cylinder. All right. Take note, the solid cylinder in this situation undergoes what we call rotational motion, but it will have no translational motion because uh, the fact that it is fixed. Okay, it is fixed in such a way that it cannot move down linearly. It can only rotate about that axis of rotation. All right. So the force that is exerted by the cable is labeled here as capital T. All right. So as the block, that end of the cable is attached to the block. So as the block is released, okay, the cable starts to unwind until it reaches uh, level 2, shown earlier in our initial illustration. So for the block, okay, there are two forces acting on it. We have of course, the tension in the cable, which happens to be the same tension that is represented in the diagram for the cylinder, right? By virtue of the third law of motion. We are able to say that these two tension forces are equal because we assume that the cable does not slip as it unwinds, all right? No slipping and no stretching. The cable that will allow us to assume that the two tensions in the cable are just equal but opposite direction. So the weight of the block, of course, is represented here by small letter mg, right? And we are asked to find the acceleration of the falling block. Okay? Definitely, it is not really falling, all right? Because it is being uh, held back by the cable. And for our succeeding computation, we will be assuming uh, two sign conventions. The rotation of the solid cylinder, okay, is said to be uh, in a counterclockwise direction. So that would be assumed to be a positive, what we call direction of the torque. of the moment of the force, the tension T. Likewise, the downward acceleration of the block will also be assumed to be in the positive direction along the y-axis. So those two assumptions will be applied in this situation. We now proceed to our computation of the two target variables a sub y and the tension capital T. We first consider the forces acting on the block. All right. So there are two forces acting on the block along the y-axis. We have the weight of the block, mg, all right, and the tension of the cable, capital T. And these two forces are in the opposite direction. Okay, we assume that the acceleration of the block in the downward direction, meaning along the y-axis, is considered to be positive. All right. So from Newton's second law, we know that this net force summation of Fy is equal to the mass of the body, the block, multiplied by that acceleration a sub y. Likewise, for the cylinder, we will consider, all right, we will consider the net torque acting on the cylinder. Okay. Earlier in the vector diagram, there are three forces acting on the cylinder, but only one of these forces actually produces a torque, and that is the torque due to the tension of the cable, right? The two other forces, the normal force directed upward and the weight of the cylinder itself, all right, do not produce torque, all right, because the line of action of those forces passes through the axis of rotation of the solid cylinder. Hence, they have no torque about that assumed axis of rotation. All right. So it's only the torque due to the tension in the cable, okay, that we call the vector sum of the torque. In this here, we label it a summation of torque along the z-axis. All right. And that is equal to the lever arm. The lever arm is in fact the radius. It is the distance from the line of action of the tension force to the axis of rotation. Okay, so we have capital R multiplied by the tension T. And we can also equate that to the product of the moment of inertia of the solid cylinder and the magnitude of the angular acceleration of the solid cylinder. This is still based on Newton's second law of motion as applied to rotational motion. And since the formula for moment of inertia of a solid cylinder is 1/2 times the mass and the square of the radius, all right, this moment of inertia is defined as the moment of inertia about the axis, which is defined as the axis, the horizontal axis at the very center, all right, horizontal. Direction of the axis is horizontal. At the very center, or shall we say center of mass of the solid cylinder. right? That's why it is 1/2 multiplied by capital M square of the radius capital R. And that will be multiplied, of course, by the component of the angular acceleration along the z-axis. All right? And since we assume that the cable, as it unwinds, all right, it doesn't slip, neither does it stretch. So the relationship between what we call the tangential acceleration, which is the linear acceleration a sub y, and the angular acceleration labeled here as alpha z, okay, such relationship will apply in the situation. Okay? The tangential acceleration is just equal to the product of the radius of the angular acceleration alpha sub z. And this is what we are going to substitute in our torque equation here. Instead of alpha z, what we are going to have is the tangential acceleration divided by the radius capital R, right? So that is substituted here. We will come up with the formula for the tension capital T, which is capital T equals 1/2 times the mass of the solid cylinder, the big M, multiplied by a sub y, right? And then, going back to the summation of the forces acting on the block, all right, and substituting in that equation, the equation for capital T, we will get mg minus, right, capital T in terms of 1/2 capital M ay equated to small m multiplied by ay. So from here, we can proceed in deriving the equation or working formula for a sub y. And that is a sub y, our target variable, is just equal to acceleration due to gravity g divided by 1 plus big M divided by 2 small m. This is the formula for determining a sub y, okay, which we are going to do in a little while. First, we also derive the formula, working formula for our other target variable, the big capital letter T. All right. So in here, we express capital T as mg minus may. Right? Expanding mg minus m instead of ay, we use this. Okay? The formula for ay we got earlier. G divided by 1 plus capital M divided by 2 small m. So, doing our derivation, or if we simplify this, we will be able to get the working equation for the tension capital T equals small mg divided by 1 plus 2 small m divided by capital M. So these two working equations for the acceleration of the block as well as the tension of the cable, okay, are what we need, okay, to answer the questions finding ay as well as the tension T. Starting with ay, all right, we substitute 9.8 meter per second squared divided by 1 plus the mass of the solid cylinder, which is 5.0 kilogram, divided by twice the mass of the smaller object, which is the block, 2.0 kilogram. And doing our math, we will get the value for ay, which is 4.4 meters per second squared. to two significant digits course. Likewise, for the tension of the cable capital T, we substitute the mass of the block 2.0 kilogram multiplied by acceleration due to gravity 9.8 meter per second squared divided by 1 plus twice the mass of the block. Alright, 2.0 kilogram, but that will be divided by the mass of the solid cylinder 5.0 kilogram. Again, doing our math, we will arrive at the value for the tension capital T, which is 6.0 newtons to two significant digits. So these are our answers to this question. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.